In this presentation, we will give you an overview of the open source console software that was developed during the MRI4ALL hackathon and give you a brief introduction into the underlying software architecture. The goal of the MRI4ALL hackathon was to develop a working open source low-field MRI scanner in just 1 week and to release everything as open source packages. The event took place in October 2023 in New York City, and it was attended by 52 participants from 16 institutions. On the right side, you can see a scheme of the created MRI scanner, which was named Sigmatron Z1. It is based on a Hallbach design made from 990 permanent magnets, resulting in a field strength of 0.043 Tesla. Most of the components have been 3D printed, and besides required components such as gradient coils and a solenoid RF coil, the scanner also has advanced features such as a cooling system and options for passive and active shimming. The components are controlled using a red pitaya board, which is a prototyping board with a field programmable gate array, which is fast enough to generate the RF pulses and to sample the MRI signal. To generate the gradient waveforms, the red pitaya board is connected to a digital to analog converter and to a gradient power amplifier via the SPI bus. Several groups have already previously used red pitaya boards for controlling low-field MRI scanners, and therefore we are able to utilize existing open source libraries provided by these groups. To run sequences on the red pitaya, we use the Marcos framework. To calculate sequences, we use the PyPulsec package, and to convert the PulseSec sequences into the Marcos format, we are using the Flocra converter. This allows us to have a host computer where the user can configure a sequence. The sequence instructions are then sent to the red pitaya running the Marcos firmware, and the recorded data is then returned to the host computer in NumPy format, where we can then perform the image reconstruction. To make sure that the scanner is easy to use, we developed an intuitive graphical user interface. This user interface is quite similar to commercial MRI products, so that users familiar with clinical MRI systems should be able to use the scanner very quickly. The software platform also provides a programming interface for implementing custom sequences and reconstruction algorithms. The source code of the software has been released as an open source software package, and therefore it can be used as software platform also for other red pitaya based scanners. And it's quite simple to customize and extend the software. Okay, let's take a closer look at the software. When you start the scanner, you first get to the registration screen where you can enter the patient information. By pressing the Phantom button, you can populate these fields with random values for a dummy scan, and then by clicking the Start Exam button, you get to the main examination screen. On the left side of the screen, you can see the sequence queue with the planned scans. On the right side, you can find controls for configuring sequence parameters and scanner settings. And on top of the screen, you can find 3 configurable viewers. You can insert a new scan into the queue by pressing the plus button, which shows a list of the sequences installed on the scanner. In the first example, we are inserting a simple RF spin echo sequence, and you can then open the settings of the sequence by clicking on the item in the sequence queue. And then you can start the sequence by pressing the checkmark button. After the scan, the acquired spin echo signal is automatically loaded into the first viewer. In the next example, we are running a turbo spin echo sequence. In this case, we are changing the echo time to 12 seconds and the echo train length to 48. And in the viewer, you can now see the expected T2 decay. By default, the software shows 3 viewers on top, but you can also switch it to show only 1 viewer to make things a little bit larger. And the viewers also provide different tools for things like zooming curves and making measurements. In the last example, we are now running an imaging sequence. The sequence used here is a 3D spin echo sequence, and we are configuring it to use a base resolution of 192 pixels and 12 slices. Furthermore, by selecting the option Plot Sequence Timing, we can review the timing diagram of the sequence after the scan. When a sequence is active, you can see an indicator at the bottom of the software that shows how long the scan will be running. When the scan is complete, the reconstruction is performed, and the images are automatically loaded into the viewers. In this case, the first viewer shows the reconstructed image volume, and you can then use the mouse to scroll between slices and zoom. And you can of course also change the image windowing. The second viewer shows the acquired K-space data. This is mostly for diagnostic purposes. And then the third viewer shows face images so that you can check if there are any unwanted face perturbations. If you want to review images from prior exams, you can do this using the study browser, which you can open with the top button on the right side. The study browser shows a chronological list of all scans done on the scanner, and you can then review the results of the individual scans. You can also load these results into the exam screen. You can review the scan parameters of prior scans, and you can also clone the scan protocol into the current exam session so that you can run this exact same scan protocol. Using the menu bar on top of the screen, you can access further functions of the software, such as a dialog to check the system status. You can open a log viewer to review system events and error messages. And then there's also a configuration dialog, which can be used, for instance, to set up DICOM nodes if you want to send images from the scanner to a PACS system. And when you're done with the scanning, you can click the exit button, which closes the exam and brings you back to the registration screen. To provide such a fluid user experience, we divided the software into 3 services that are running as separate processes. These services are completely decoupled, and they communicate only through a task queue as well as an IPC mechanism for status notifications. The UI service provides the user interface for configuring scans, and when a scan is started, it places a scan task in the task queue, and then the acquisition service takes this task, calculates the sequence using PulseSec, and then it runs the sequence instructions on the Raspberry board using the Marcos framework. And after the scan, it places the task with the collected raw data back into the queue so that the reconstruction service can then continue with calculating the DICOM images, which are in the end passed to the UI service for visualization. And this very modular architecture makes it very easy to debug the software, and it also allowed us during the hackathon to work on these different functions in parallel. In the spirit of the MRI4ALL hackathon, the software has been developed using only open source components, and everything has been written in Python. The operating system is Ubuntu 22.04. The user interface has been developed using PyQt5 together with Matplotlib and PyQt for the data visualization, and as mentioned, we used PyPulseSec and Marcos for the scanner control. And then we used a number of helper libraries for the image calculation, such as NumPy, PyDICOM, and the Office DICOM toolkit. Moreover, we are also providing a standardized development environment which is easy to use and integrates with Visual Studio Code and Qt Creator for code editing. The development environment can be fully automatically installed inside a virtual machine using Vagrant and VirtualBox, and you can find the detailed instructions how to do that on our GitHub wiki. The required steps are first to clone our GitHub repository onto your computer, then to create a new virtual machine by typing Vagrant up, which will install the complete software inside the VM, and then you can connect Visual Studio Code to the virtual machine for code editing. And lastly, you can then also start an X11 shell for testing the user interface inside the virtual machine, so you have a complete test environment. The software is installed into the folder /opt/MRI4ALL. This folder has several subfolders. The subfolder console contains the application code, the subfolder config contains the system configuration, and the subfolder data contains all the scan data. This data folder again has multiple subfolders which are used for the task queuing. When a new scan is planned, a folder with the scan definition is created in the acquisition queue. When it's ready for scanning, the task is moved to the acquisition folder, and after the acquisition, it is placed in the reconstruction queue. When the reconstruction service is then ready, it places the task in the recon folder, And at the end, after the reconstruction, the task is moved to the complete folder. And when the user ends the exam, the task is moved to the archive folder. So as you can see, these folders are used to manage the state of the scanner. Each scan has a separate subfolder with a name that is composed of a unique exam ID and a scan counter. Inside this folder, you will find a file called task.json. This file contains the definition of the scan tasks with information such as the requested sequence type, sequence parameters, and system information. The subfolder sec contains the sequence instructions in the pulsec format. The folder raw data contains the acquired raw data in the NumPy format. These two folders are populated by the acquisition service. And the subfolder DICOM contains the DICOM images, which are placed there by the reconstruction service. An advantage of this file-based state management is that it makes it very easy to test individual service functions. For example, if you are working on a new reconstruction algorithm, you can take an existing scan folder from a previous scan and pass it manually to the reconstruction service. And you can do that in the dev environment without actually sitting at the scanner. The MRI4ALL console software comes with several example sequences. If you want to integrate your own custom sequence, you need to create a new Python file in the folder opt MRI4ALL console sequences. Inside this file, you need to define a Python class that is derived from the sequence base class, and then you need to implement a number of methods. These methods are used as API interface for tasks including instantiation, state management, UI definition, sequence calculation, and sequence execution. And you can find more information about the meaning of these individual methods on our website. If you want to integrate new reconstruction techniques into the software, you can register these algorithms in the Python file that is listed on this slide. Reconstruction algorithms are expected to read the acquired raw data in the NumPy format and to write out the reconstructed images in the DICOM format. And scan and reconstruction parameters can be obtained from the scan task file in the JSON format. Reconstruction algorithms are allowed to generate multiple image series, curves, or other type of binary data. It is important, however, to list all created results in the scan task file so that the UI service knows about these results. And you can also specify which results should be automatically shown in the different viewers of the software. To summarize, the console software developed for the MRI4ALL scanner provides a user experience that is similar to clinical MRI systems. However, it is fully open source and has been written in the Python language. Therefore, it is very easy to modify and to extend, and it can be used as software platform for other custom-built MRI scanners based on Red Pitaya boards. If you want to learn more about the software or about the MRI4ALL project, please visit our website at MRI4ALL.org. Thank you for watching.